Hello! So today we're going to be finding the roots of a quadratic equation. My name is Prishirati and I'll be conducting this mini lesson today. So first, let's clarify a couple of things. So what is a quadratic? So a quadratic equation is essentially any polynomial equation in which the highest power of x is 2. So essentially, if you look at x, it'll have this little subscript above it, and the highest number that can be in that subscript space is 2. So what is a root? So a quadratic equation is usually one of those polynomials that I talked about, set equal to 0. A root is the solution to that equation, what x equals, when we want to have that entire polynomial equal to 0. So here's an example. Let's say we have x squared plus 6x plus 9. So we can tell that this is a quadratic because we have x squared over here. The highest number that can be, the highest and only number that can be in that subscript space is 2. And the quadratic equation means that this whole thing is equal to 0. And the root is essentially what x equals if this whole thing is true. So what we'll learn today. There are two algebraic methods to solving a quadratic equation. There's the quadratic formula and factoring. Usually the other method that we would have used to solve a quadratic equation is we'd graph our quadratic and we'd figure out where it intersects the x-axis. So we have here and here. But sometimes we don't have access to a graphing calculator, or we simply don't know how to graph one specific quadratic equation. So it's better to use one of these algebraic methods because it'll be a little bit easier to wrap your head around. Each algebraic method has a specific context in which it should be used. There's pros and cons to each. There's sometimes one is easier and one is harder, but there's other times that's flip-flopped. So you'll learn about that context. And each has some fun tricks to help you learn the method better. So let's get started. The quadratic formula. It's tried and true. It works for pretty much every quadratic, and you can even calculate complex roots when a function has a root containing the imaginary number I. So imaginary numbers and complex roots, you'll kind of encounter them a little bit later on in your math career, but I'm going to tell you about them now because if you know that the quadratic formula can be used to calculate complex roots, it'll make it a little bit easier for you. I'll explain what a complex root is a little bit later on, but just know that quadratic formula can be used to calculate complex roots. The downside of this omnipotent formula is that it is time-consuming, slow, and hard to do without a calculator. If you, when we look at that formula on the other slide, we'll see that there's actually a square root. So if you don't end up with like a nice pretty square within that square root, we're going to end up with something that'll give us a lot of decimals. And if we don't have a calculator, it's going to be really hard to calculate that square root. So therefore, I only suggest using it for unfactorable quadratics. An unfactorable quadratic is essentially a quadratic that the other method of algebraic solving doesn't apply to. So we would use it as our kind of last resort, tried and true method. So here's the quadratic formula. Negative b plus or minus the square root of b squared minus 4ac all over 2a. Although it looks scary to memorize, I promise it's quite simple. There's a bunch of ways to memorize this, but the best way I find is kind of a musical device to help me remember. I like memorizing it to the tune of Pop Goes the Weasel, because I think that's what it connects best with. And I will sing it badly for you now, but here's about how the tune goes. Negative b plus or minus the square root of b squared minus 4ac and over 2a. That's the quadratic formula. Although you can probably sing it better than I can. Essentially, this little device kind of helps you keep straight what's negative, what's squared, and what's going over what. So it makes the whole thing a little bit easier to memorize. I'd also like to point out to you what these letters mean, because it might be completely weird to look at on first glance. So let's say our quadratic equation is x squared plus 6x plus 9, like earlier. So a is essentially the coefficient of this x squared term. So a is essentially that number that's right next to it. Since there's no number next to x squared right here, we can assume that a is 1, because we would multiply x squared by 1 in order to get x squared. B is the coefficient next to the x term. Since we can see that there's a 6 next to it, we know that b is 6. C is that constant term. It's essentially that term that does not have any x next to it, no variables. So in this case, C is 9. And if you don't see an x term or you don't see a constant term, you can assume that the corresponding symbol is 0. So if there's no x term, assume that b is 0. If there's no constant term, assume that c is 0. And then you can plug all those letters into this equation and solve for your roots. So explaining complex roots a little bit more. So the imaginary number I is the square root of -1. So as you can tell, if I write it out a little bit, there's nothing in our regular number system that can give us this value. Because remember, a square root is essentially multiplying a number times another number to get another number. And that's, okay, so a number times a number equals another number, that's a square. And if we want to do the opposite of it, we'd essentially want to figure out the two same numbers that multiply to get our bigger number within the square root. Unfortunately, there's no two same numbers that multiply to get us -1, therefore this square root doesn't really exist. And the thing is, since any roots that contain this I don't exist either, we can't actually see these roots on our coordinate plane. So if I draw out my coordinate plane here, a regular quadratic equation will look like this. We see our roots, everything's good, everything looks fine. But if we have imaginary roots, our quadratic equation might look something like this. We don't actually see where our quadratic equation hits our x-axis, and then we don't really know where exactly our imaginary roots are. So if the part under the square root in your quadratic equation is negative, you will have a square complex root on your hands, since it will involve some variant of I. You'll learn about complex numbers a little bit later on in your math career, but it's good to be familiar with them now because they'll come in handy later. Method is factoring. It's easy, very fast, can be done without a calculator, but it can only be done on expressions that factor into whole numbers. So essentially what that means is that when you use factoring, I'll use the example I've been using for this entire time, x squared plus 6x equals 9, x squared plus 6x plus 9. This means that we can actually factor it into nice, pretty whole numbers. This would actually be x plus 3 times x plus 3, or x plus 3 squared. So this type of factoring, it can only be done if this equation can factor into pretty numbers. Sometimes you kind of just have to try factoring, and if it doesn't work, you will resort to using the quadratic equation. So usually it depends on the context, because sometimes a problem will not give you the opportunity to use a calculator. That might be a big clue into whether you should use factoring. Or sometimes your question will definitely have to be answered in whole numbers, in which case that's a pretty big hint that you probably should try factoring first. So there's a lot of examples that we need to use with factoring just to get familiar with them. Just to get familiar with it, I'm going to give you a couple just so that you can see how exactly factoring works. So to factor this quadratic equation, x squared minus 5x plus 6, we need to find two numbers that add together to get -5 and multiply together to get 6. Since we add to get a negative number and multiply to get a positive number, both our numbers must be negative, because a negative times negative equals a positive, and a negative plus a negative equals a negative. So let's go through all the numbers that add to -5, and all the numbers that multiply to get 6, whichever is less work, and use those numbers to do the other operation. So multiply if you added and vice versa. So in this case, so here's how I would go about this. Usually the numbers that multiply to get 6, they're easier to find because there's only a couple numbers that would multiply to get 6. So that's what I'm going to go with. The only numbers that multiply to get 6 are 1 and 6, and 2 and 3, and then all the vice versas. So 6 and 1, 3 and 2. So that's only 4 numbers. So now we can take those 4 numbers and we can see if the pairs add together to get 5. So we have 1 and 6 as our first pair. We can see that they add together to get 7. So we know that that pair is not going to work. We also have 2 and 3. We know that if we add them together, we're going to get 5. So that pair seems to work if that 2 and 3 are negative. So that way it abides by this add together to get -5 and multiply to be 6 rule. So -2 and 3 should be our factors. And as I said, yep, those factors should be -2 and 3. And you'd want to put them in this factored form. Essentially what that means is 2 sets of parentheses enclosing equate two factors. So we'd have x minus 2 and x minus 3. Essentially add the factors to x and then multiply to the other factor where you've added x to the other factor. And now the last example, there's a couple more that we might need to use later on, but I'm just going to go into this one as a kind of a brief dip into what factoring is. So to factor, you must find the two numbers that add together to be -9 and multiply to be -22. Sorry, that's a little bit of a typo on my part. Since we add to get a negative number and we multiply to get a negative number, we must have one negative number and one positive number because negative times positive is negative. And since we have a negative number here, that means that our negative number must be bigger than our positive number. It must have a bigger absolute value. So now we need to go through all the numbers that add to get -9 or all the numbers that multiply to get -22, whichever is less work, and use those numbers to do the other operation. So let's go through all the numbers that multiply to get -22 because usually that's a little bit easier to do than to get -9. So the first pair I can think of is -22 and let's say 1 because -22 times 1 is -22 and our negative absolute value is bigger than our positive absolute value, but when we add them together we get -21, which doesn't seem exactly correct. So let's try the next pair. We have, let's try -11 and +2. Our negatives have a bigger absolute value, so this looks like an okay shot. And if we add them together, we do get -9. So this seems like the best option for our factors. And as I do say there, we end up with -11 and 2. We add them to x for both of our factors, we multiply them together, and we're done. Thank you for listening, and have a wonderful day.